Hello everyone, I'm Jamie Hollands and I would like to introduce you to our Capstone project. Volvo 240 Modernisation, updating the Volvo 240 electrical system using a controller area network. Our technical directors are Mike Smith, an electrical engineer and a graduate of the University of Rhode Island, and Brendan Smurbeck, a computer engineer and a graduate of the University of Rhode Island. Our team is comprised of 3 electrical engineers and 1 computer engineer. Cameron Major, Electrical Engineering, Jamie Hollands, Computer Engineering, Spencer Kubicki, Electrical Engineering, and Timothy King II, Electrical Engineering. Company Overview. We're a student-led capstone project. The idea to update the Volvo 240's electrical system has been a passion project of mine for a few years. Dr. Sunak thought it would be an interesting idea to pursue for a capstone project. He has built a team of young engineers with a shared interest looking for a challenge. Although we are officially not a company, there is potential for us to start a company in the future. Project motivation. Automotive standards for electronics are high. Building circuits to these standards would be a great learning opportunity. We will also learn the widely used controller area network protocol and keep as many of these beautiful vehicles on the road as possible. Anticipated best outcome. The anticipated best outcome is to produce a functional prototype controller area network for the Volvo 240 series. The prototype should be able to process all required switches and signals that exist on the original 1993 Volvo 240 electrical system. It should also include fault identification and increased vehicle data resolution. The vehicle systems will be split across multiple computers that communicate using the CAN protocol. Finally, all the vehicle data will be visible from a digital display that will replace the current analog instrument cluster. Summary of team accomplishments. Collected and organized all vehicle data, created test circuits to emulate vehicle behavior, designed circuits that interface with our test circuits, sent and received data on all nodes on the CAN bus, and controlled our test circuits using our controller area network. Economic impact. We could potentially create a company and provide this or a similar opportunity for future capstone students. Overview. We have a 4-node CAN system, 1 node for the dashboard and digital display, 3 nodes to control and sense vehicle signals. Individual technical accomplishments. I am responsible for the initial idea and design of this project. However, over the course of the first semester, my team members and I have significantly modified the design to its current layout, a 4-node CAN bus. I made the initial selection for our microcontrollers. The Arduino Mega had enough power and general purpose input-output pins, as well as the selection of available CAN peripherals. The Arduinos would power 3 of the 4 nodes on the vehicle, with the last node being powered by a Raspberry Pi 4. The Raspberry Pi 4 was selected so that we could utilize Linux to develop a graphical instrument cluster to replace the vehicle's current instrument cluster. The Raspberry Pi is powerful enough to communicate on the CAN bus while displaying vehicle information on a 7-inch LCD display. While the electrical engineers on our team developed circuits to sense vehicle information, I was responsible for having all these circuits communicate on the CAN bus. To do this, I used the seed Arduino CAN library on the Arduinos and libgiod, rpi.gpio, socketcan, and Fedora 35 on the Raspberry Pi. For putting together a prototype, I developed the Raspberry Pi interface using Python. I made this decision so that I could develop all the required software at the cost of a small amount of performance. Once the entire prototype is complete, I would take a lower level approach to recover some of the performance losses. Defining CAN frames correctly requires ordering vehicle information from the least important to most important. When CAN frames are put on the CAN bus, they go through a process called arbitration. As an example, if 2 CAN frames are put on the bus at the same time, with the arbitration IDs of 00000000 and 11111111, then the node with the ID of all zeros will gain control of the bus. This is because in the CAN protocol, zeros are dominant. If we pretend that the frame with the ID of all ones was notifying the vehicle that a reverse light bulb had failed, and the frame with the ID of all zeros was notifying the vehicle that the engine had lost pressure, you would want the oil pressure message to propagate first. To meet ABO, interface all the completed nodes together on a canvas and create a basic interface to view all vehicle data. Up next is Cameron Major.
Thank you, Jamie. My name is Cam Major, and I am one of the 3 ELEs on this project, along with Spencer and Tim. The bulk of our progress on the project can be divided into 2 portions, before and after our individual node assignment. We are designing 4 nodes, with 1 at the dash, 2 in the front of the car, and 1 in the back. Each ELE has responsibility for one of the latter 3 nodes, which means designing the hardware, helping Jamie define the necessary operations of the Arduino on that node, and assembling the node protoboard. While many of us have components on other nodes besides our own, the node assignment allows us to specialize and gain a deeper understanding of specific location-based requirements. We did a lot of work prior to the node assignment, mostly demonstrating and exploring the individual signals from the car, such as gauges, lights, and more, in order to fully understand the requirements of our final designs. This work, while not going into the final prototype, was instrumental in our subsequent circuit design. My individual node is responsible for driving all of the exterior lights of the car, by a process that I will go into more detail on in the following slides. My node will function primarily as a receiver due to the nature of the light circuits. When the driver flips a switch on the dash, whether it be for headlights, blinkers, or anything of the like, a signal will be sent from the dash node over CAN to my node. The Arduino on my node will send a pair of pulses to an H-bridge IC, which will provide an output current in one direction or the other to latch or unlatch a relay, which will turn the light on or off, depending on what was requested by the driver. My node is responsible for driving 4 sets of lights, the high and low beams in the front of the car, and each directional indicator. The low beam signal will also be sent to the running lights as the 2 operate simultaneously. Because of this, I will be using 2 dual H-bridge ICs, whose outputs will be spread to a relay bank consisting of 4 latching relays, and those relays will run directly to each light. A nearly identical version of this circuitry will be placed on Tim's node to drive the lights in the back of the car. Here I have a few examples of the general lab work I have assisted with, mostly consisting of circuit design, testing, and soldering down circuit components. In order to meet our anticipated best outcome, I will need to finalize my node protoboard, along with any testing and troubleshooting that may occur. Our biggest hurdle on this front is providing consideration for flyback current in the H-bridge ICs. I recently designed a protection circuit to account for this with the use of 4 diodes per signal, and once the parts come in, finishing the protoboard should be a matter of simply assembling, testing, and soldering down the final product. Should we exceed our anticipated best outcome, I will be assisting the other ELEs with PCB design and implementation, applying our designs to the car, and any testing or troubleshooting required along the way. And on that note, it is with great pleasure that I introduce our next ELE to speak, Spencer Kubicki.
Thanks, Cam. Hello, I'm Spencer. I'm an electrical engineer who worked primarily on circuit design and soldering. My largest contributions to the project have been the design and soldering of the fuel and coolant temp gauge test circuits, and the design, implementation, and assistance with software for a bulb failure circuit. I also assisted my teammates with their individual projects whenever needed, as well as testing and research into the different components on the Volvo 240 dashboard. Pictured on the left is the fuel and coolant temp gauge circuit, consisting of potentiometers to simulate the changing resistance values determined by the amount of remaining fuel and the temperature of the engine, respectively. Both circuits have been soldered to the same protoboard for testing purposes, but can and will eventually be separated for the final implementation of the nodes. Pictured on the right is an early design of the bulb failure circuit. The logic behind this test circuit is to simulate a blown bulb in the vehicle by pulling out an LED to create an open circuit and recording the change in voltage to the analog-digital converter chip. The LEDs are connecting to the power source to each of the input pins of the chip, and when they are removed, the pin is grounded by a pull-down resistor, changing the voltage on the pin to 0. The chip sends a message to the node's microcontroller when prompted, and if the microcontroller detects a change on one of the pins, it will display specifically which bulb is blown. These test circuits, both designed by Cam Major, were soldered by me, as were the fuel and coolant temp circuits. In order to achieve the anticipated best outcome, I'll be finishing the design and eventual soldering of my designated node, the front left node of the vehicle, and implementing my bulb failure circuit on all lights in the vehicle. In the likely event we surpass our ABO, I'll be excited to begin the process of implementing the circuits we designed into an actual Volvo 240 and designing PCBs of our nodes for easier and safer implementation. With that, I'd like to pass things off to my teammate Timothy King.
Thank you, Spencer. My individual technical accomplishments fall into two categories, the first of which deals with the legacy cluster. The first thing that we did for the project was take a look at the legacy cluster and define all the signals that it takes in and all the information that it displays. And next we started figuring out how those systems work and what the signals that it takes in look like. And we did that so that way we could build circuits that replicate signals from the car for our own testing. Pictured is a picture of the legacy cluster. My other technical accomplishments deal with our CAN system and the proprietary cluster that we're designing. I derived mathematical relationships that link physical data to electric data. That is, monitoring a physical system. We can define how it works mathematically so we know what to expect when we take data from it electrically. I also assisted in planning the architecture of the system and some of the hardware that we would use, and making sure that it would meet our requirements for sending data over the CAN network. I selected and implemented solutions for sending and receiving signals, and I think that this is where my large technical accomplishment exists. I'd say that my largest technical accomplishment is designing a circuit that converts frequency to voltage. The frequency is the frequency of a signal that is related to the engine RPM, and it generates a voltage that can be sampled by one of our microcontrollers in Arduino. The CAN node that I'm individually responsible for designing is the rear CAN node. The rear CAN node's job is to read sensors like the fuel level sensor and the vehicle speed sensor and interpret that information and put it on the CAN bus. There will be also a circuitry to drive the external rear lights and a bulb failure sensing circuit to sense failures in external light bulbs in the rear. To meet our project's anticipated best outcome, I'm expected to design, assemble, and troubleshoot a circuit similar to the one I designed for the tachometer that processes the speedometer signal. I will also be responsible for addressing onboard power conversion needs. And finally, I will assist in hardware design and general improvements to other electronic circuits in the car. If our ABO is met, I'm responsible for migrating contents of protoboards to printed circuit boards and developing mounting solutions that will enable testing to see if we can meet automotive standards. Throughout the fall semester, we've been tracking several risks related to our project. Initially, we thought that the chip shortage would have the most significant and adverse effects on our project. But as we've worked on the project, we've realized that we've had no problem obtaining the chips that we need, and we're designing around what's in stock. So we've downgraded the severity of the chip shortage risk to medium. COVID is still a very real risk, but with low likelihood and low impact, because our team takes all the necessary steps to ensure that we stay healthy, and working remotely is still an option. And finally, there were some risks involved, with some risks centered around the fact that our project is student-led and student-defined. So if we had defined something unattainable in a certain time frame, it could have adverse effects on our project and our final outcome. Finally, we would like to acknowledge everyone that has contributed to the Capstone program, including Dr. Sunak, Mike Smith, Brendan Smirbeck, and Jack Morphy. All of these individuals have contributed greatly to the success of our project.